Good afternoon, class. Quick review of where we were last class before we move on. I'm excited that the last couple classes we finally have gotten to that thing called electricity, not just static electricity. Static electricity is fun for lightning and making your hair stand up. That's about it. When we think about modern life, most of what we're doing, even driving our car, all of our laptops and cell phones and computers and the lights in this room and our toaster and everything, including our own bodies, run off electricity. So it's a worthwhile topic to talk about and to understand, hopefully. Hopefully you can understand a little bit about how that works. And the basic principle behind how it works is pretty straightforward. And so we started talking about it last class, or maybe even a little bit on Friday, and that is this. All electric circuits, my brain, my muscles, my laptop, my cell phone, all electric circuits go like this. You need a source of electromotive force. That's just a fancy word for voltage. You need a source of electric potential. That's called voltage. You need something to lift some charges above ground and then take advantage of them as they fall back to ground. Before we discovered electricity, I think maybe we had things like water mills or something. We were kind of doing the same thing. Get some stuff above ground and then take advantage of it as it falls back to ground. That's what the power company does all day long. Their job is to lift stuff above ground, and so we can do work, literally do work as it comes back to ground. So somebody's doing work to get those charges above ground, and then we're doing work when we light up our laptop screens or send a text message as those things fall back to ground. So it's not much more complicated than that. It's literally just taking stuff above ground and then taking advantage of it as it falls back to ground. In the case of electricity, the thing we're lifting above ground is electrons. And so we've seen that's about the simplest circuit I can make right there. Let's see if I zoom in a little bit. Zoom in a little bit on my circuit board over here, on my light bulb board. Here's my simplest circuit I think I can make. Here's a light bulb screwed in, and this is called a series circuit, and I just have my source of voltage. That's the power company. That's my source of potential. So the power company's job is to take these charges and lift them above ground. And then as the circuit designer, I get to decide where they go. And so they're going to run through this light bulb and then through these two, these are short circuits. These are just pieces of wire. So I'm going to lift the charges above ground. I'm going to route them through this light bulb. Then they're going to take two short circuits back to ground. Now I could screw these two light bulbs in over here. Notice no current is running through these over here because I have right here what's called a short circuit. Let's see, if I were to even take that short out, I don't know if you, yeah, I don't know, can you tell those are even on? I'm going to turn the lights down a little bit. That's not down. Can you even tell that those lights are kind of on right now? I don't know if we can see that. On. Okay. Let's see. Yeah, you can tell. Okay, see the difference? They're on a little bit. They're on, and now they're off. Okay. So I've got current running through those two. Now, if I were to plug in this short circuit, they're going to go out. The reason they're going to go out is because I have almost no resistance right here. And so all of the current is going, well, not all, almost all, the vast majority of the current is going to go through my little short circuit right here. So I mentioned last class, I think we've heard the phrase, electricity takes the path of least resistance. When I unplug this short, the path of least resistance is both of those light bulbs. So the path of least resistance is both of those light bulbs. This short is not in the circuit right now, so I've got current that is going through this bulb, and it wants to get to ground, and it's going through both of those bulbs. If I were to take one of those out of the picture, it's going to have to go through, it's going to only go through this one. So right now, I've got current going from this bulb. This is not plugged in. This is not plugged in. So it has to go through this outer bulb and back to ground. And you can see how much is going through by the brightness. By the way, I should mention, notice both of these are both 60-watt bulbs right now, so they both should be roughly equal brightness. Notice what happens to this bulb, this one here, when I plug in another bulb. When I plug in another bulb, and here's what I want you to notice. The current, here's my source of current, here's my voltage right here. All of my voltage has to go through, or all my current all of my current has to go through this bulb, this first bulb. And so over here, I've got another bulb plugged in, and it's going back to ground. So I just have one series circuit. When I plug another parallel bulb in, watch what happens to the brightness. It goes up. It doubles, roughly. It roughly doubles because all of the current is still going through this one, and now it's being split over here. I'm drawing more current over here. I'm drawing more current. So I can plug 100 light bulbs all in series, or all in parallel. These two are in parallel. I can plug 100 light bulbs all in parallel, and I can turn them all on, and they all see the same voltage. And there's a thought maybe, wow, you're getting like free electricity or free voltage because you can plug 100 bulbs in with just one source. Yes, that's great. I do pay for it. The power company doesn't just charge me for voltage. They charge me for the amount of power I use, and everything I plug in parallel is going to draw more current. So the brightness of this bulb right now is sort of indicating how much current I'm drawing through my circuit. So this bulb, the brightness shows how much is being pulled from the power company, and I'm going to pull less if I only have one other bulb in the circuit. So I put another one in parallel, I'm going to draw more. And I take them all out. Of course, I'm not. Now I just have a bunch of open circuits. So there's no path to ground. I still have 120 volts on the left side of this bulb, but there's no path to ground, so it's not going to turn on. And if I plug in this short circuit, now there's a nice path to ground, and it's going in a series circuit. Okay. I think that's all I wanted us to see about parallel circuits and series circuits. So really what I have right now is two bulbs in parallel. That parallel combination is in series with this guy. Those are the two ways you can plug in electrical components. They're in series, which means you have to go from one to the other, or in parallel, just meaning you have two options. So an electron that made it to this junction right here has two routes it can go. It can go through this bulb or this bulb back to ground. And that's literally what happens. Electrons stream through the circuit, and they get diverted. So again, maybe thinking about plumbing helps. You can imagine if you have plumbing elements in series, water that goes through one has to go through the next. But then it gets to a junction. Water either goes through one or the other. It doesn't go through both. And so literally the amount of electrons, the amount of water, whatever, splits. Julia. To make them brighter? Because right now they're both pretty dim. Yeah, Julia, that's a good question. So right now I've got these two guys pretty dull, and here's why. I've got a lot of current going through this one. And so most of this 120 is being dropped. I don't know if that's a term I've used yet. When we talk about voltage, we do think of it in terms of altitude. So there's ground, there's high voltage, and anytime you go through a resistive element, you drop voltage. And so there's 120 volts here. Most of it is being dropped across this bulb, and not much is left for these guys. So these guys are both seeing the same voltage, but it's low. So if I were to take this bulb out and replace it with the short, I now have two bulbs, both in parallel. Both are seeing 120 volts. Nothing's been dropped over here. In fact, I can get, and here's where it looks like you're getting free voltage. Look, I can make three bulbs all really bright. All three bulbs are seeing 120 volts because the power company is doing their job. There's 120 volts up here and ground down here. All three bulbs are seeing 120 volts, and all are nice and bright, but I'm paying for it because each one is drawing current. And so I've got a lot of current. I'm pulling a lot of current right now. Now, this is plugged into the power company, which is plugged into a fuse box somewhere. And if you've ever opened up a fuse box, there's little numbers on the breakers. Like, it's usually a breaker box nowadays, not actual fuses. That number is how much current you can draw. And every time I plug in something additional, I'm drawing more current. So this guy's drawing current, and this guy's drawing current, and this guy's drawing current. And the more I plug in, eventually I plug in now my toaster, and then my microwave, and then my hair dryer, and my vacuum. Eventually I just blow the circuit, and I have to go flip the breaker. Back in the day, you would blow a fuse, and you'd had to go replace the fuse. Now you just flip a little switch. Hopefully, again, I mentioned before, in any electrical circuit, you usually want to plan where it's going to blow when it blows, because it'll blow. Okay. Any other questions? Great. I think that's all we need to know right now about circuits. So there's my simple, that's my just simplest circuit. Here I have two resistors or 2 light bulbs, whatever it is, 2 hair dryers in series, so each is seeing half the voltage drop. If those 2 resistors are equal, they're both going to see the same. They're both going to see half. So 120 volt circuit, they're both going to see 60. If I hook 2 in parallel, notice both see the full drop. Both of those light bulbs or hair dryers, whatever they are, both are seeing the full 120, and they're nice and bright, but I'm pulling more current. And that's all we need to know about that. So that right there is a DC circuit. So far what we've been talking about is DC current, direct current. That's redundant. So we've been talking about DC, direct current. That is a lot of stuff. So if we're talking about DC current gets us pretty far. DC current or DC circuits, that's your cell phone, that's your laptop, that's, I don't know, in here, yeah, that's a lot of stuff. Anything that runs on a battery is going to be DC. That's a pretty good rule. If it's running on a battery, it's going to be DC, because this is what batteries do. They just trickle out charge. That's their job. They just send out charge. That's a lot of things. Think about the battery-powered things in your life. Those are using DC. There's another set of circuits we have to talk about called AC. But to get to AC, we have to take a long road through the magic of magnets to get us to AC. So what we've talked about so far is DC circuits, and I would love to move on to AC circuits. AC circuits are when you plug something into the wall in just about any wall on the planet, what's on the other end of that plug is AC, or alternating current. To understand how alternating current works and why we use it, we're going to take a long road, maybe a multi-day road, through the wonders of magnets to get us to AC. So we'll get back to circuits, but we're going to have to talk about magnets first. Hopefully everyone has seen that Miracles video. If you haven't, definitely this afternoon Google Insane Clown Posse. That's the Insane Clown Posse there. That is Violent J and Shaggy 2, number 2, Dope. That's the Insane Clown Posse. They came out with a song, I forget, it was like 5 years ago or something, called Miracles. I don't know if you guys seen this. It was amazing. You just look it up on YouTube. It's amazing. But here's some of the lyrics. I see miracles all around me. Stop and look around. It's all astounding. So far, great. Water, fire, air, and dirt. Sure, those count as miracles. Effing magnets. How do they work? And so the song is just, and the video is amazing also. It's all about just all the wonders of the world around them. And they were just astounded by magnets. And my first thought is, okay, magnets are a little bit mysterious. You might want to talk to, oh, nope. They're not going to talk to a scientist. So I don't know where they're going to get their information on magnets. But, so here's the good news. Scientists have figured it out. We know how magnets work. It's not a mystery. It's cool. It's kind of neat. They repel each other at a distance, which I think should be a little bit astounding. The fact that these two magnets know each other exists from a distance, I think that's really cool. But we physicists have pretty much figured out the mechanism, and it's less miraculous maybe than you think, but let's talk about it. And again, this is a long road to get us back to circuits. So to understand magnets, we have to remember that there's these things in the universe called fields. Remember, masses create gravitational fields. And a mass creates a gravitational field which pulls and pushes on other masses. We've got electric charge. Charge creates electric field which pushes and pulls on other electric charges. Magnets create a field, but they're not like that picture. And they're not like that picture because, so B is for magnetic field. So that part's true. So we've got what? Gravitational field, electric field, magnetic field. And there's my north and my south. But here's why they don't work that way. These first two pictures are for fundamental properties of the universe. Mass is a fundamental property of the universe, and you can take a mass, put it in an empty universe, and you get this nice radial field all around it. Electric charge is a fundamental property of the universe. You can put an electric charge in the middle of an empty universe, and you get this nice radial electric field that just shoots out in straight lines to infinity. Turns out magnetism is not a fundamental property of the universe. It arises from moving or for now, let's just say it arises from moving electric charges. And I think when Faraday or whoever figured that out, that was pretty mind-blowing. So you can imagine most of human history, there's this thing called electricity, lightning, static cling, whatever. There's this stuff called magnetism. It comes from a place called, I think it's Magnesia or something like that. That's where they first discovered these rocks that had this property. They stick together. And it would be understandable to have like two rocks that stick together and lightning and not think they're related. It was Faraday and Maxwell and some guys like late 1800s that figured out that actually electricity and magnetism are actually interrelated in something we now refer to and understand as electromagnetism. And so actually, I could even start there and remind you that for a while we were talking about photons. Photons are electromagnetic waves. So far we've really only just talked about the electro part, but a photon is an electromagnetic wave. And the reason it's a self-propagating electromagnetic wave, the reason it does that is because one creates the other. An electric field creates a magnetic field. A moving or changing electric field creates a magnetic field, and vice versa. And so when we see magnetism, we don't see it like this, because it's not a fundamental charge. We see it arising from moving electric charges. And just like, as we've been talking about circuits, that charge that I'm talking about is usually an electron. So electrons are the fundamental charge carriers in the universe, and they're responsible for stuff like electricity. They're also responsible for magnetism. And so magnets, how do they work? They come from moving electrons, or they just come from, we'll say moving electrons. And so you can actually create this thing called magnetism from electrons. So the field doesn't look like that. It looks more like that. It looks more like that. And that's hopefully a familiar picture to us. Hopefully you've seen the picture of a north-south magnet. Let's see. Let's take a look at some pictures of that. So let's go to that camera. Okay, I have up here a little container full of iron filings. Iron filings are magnetic. We've probably played with that before. And right now they're all kind of jumbled around, but if I put a magnet nearby, that magnet might be strong enough. I might need to get a stronger one. That magnet might be strong enough to align some of the iron filings in the vicinity of that magnet. And if that one's not strong enough, I can definitely use this guy. Here's a bunch of tiny little compass needles, and they align to the magnetic field. So right now you're looking at a picture that looks very similar to that. Again, when we draw these magnetic field lines, we're drawing a convention, really. And that convention is the arrows point in the direction a north would feel. And so there's no such thing, we don't think. We might discover one day. We don't think there's such thing as just an isolated north. But if you can imagine what just a little north would feel like, a north would be repelled by another north and would be attracted by a south. So that's what those lines indicate. And that's what these little compass needles are indicating. So you can see as I rotate this guy, those little compass needles are aligning to that magnetic field. So what I have here, what you're looking at, this picture that's up on the board, it's also right here, is sometimes called a permanent magnet. And I think you might pick up one of these or even find a rock that exhibited magnetic properties. You might think, oh, that is a property of the material. There are certain things that are just magnetic. Magnets are magnetic. They're not. What's happening is that this magnet, just like everything else in the universe, is made of matter which has electrons in it. You and I are, how many magnets do we have? We have like 7 billion magnets inside us. Every one of our electrons can function as a magnet. In fact, does function as a magnet. An electron is charged. We know that. -1 sometimes. And it's moving. That's enough. That's all you need. If you have an electron, it's charged, and it's moving, it's a little magnet. Any moving electric charge creates a magnetic field. The only reason I am not stuck to all the paper clips in the room is that all my electrons are all just kind of randomly jumbled, and they all cancel out. So I'm made of billions and billions and billions of magnets, and so are you, but all of your magnets are just in different directions and they all cancel out. Maybe that's what this is for. Let's see if this one works. This one is not as strong because I've got two that are kind of canceling each other out. And you can see the field is a lot stronger on something like that. Okay, so there are materials in our world that we can actually cause all the electrons to line up, and that's called a permanent magnet. So if you've ever picked up like a refrigerator magnet or anything you might call a permanent magnet, that's all that is going on in there, is that the electrons, just like you have, they're all magnets, just like your electrons are magnets, but we've somehow aligned them. And usually the way we do that is subject them to a strong magnetic field. So if I'm at the magnet factory, I've got a really strong magnet. As the magnets are coming off the line, I'm just hitting them with a super strong magnetic field, and that's aligning them, and certain materials will actually keep that alignment. And I don't know if there's such thing as a permanent magnet. Electrons jiggle all the time. Eventually they might jiggle themselves loose, but it might be the lifetime of the universe or something before that happens, if it's a good one. But that's all they were doing, is aligning them. Now, some of the first magnets we found, probably as the Earth was cooling, or the volcano that they came out of was cooling, they were subjected to the Earth's magnetic field, and that aligned them. But you need some way to align the electrons to get them all kind of pointing in the same direction, and you have a permanent magnet. Okay. So that's the quick version of where magnets come from. They come from moving electric charges, stuff like electrons. In our everyday life, let's do that guy. In our everyday life, where we get a lot of magnets is not relying on things like permanent magnets. We rely on electric field, or we rely on electric current. So, like I said, magnetism arises from moving electric charge. One way you get that is just the fact that everything has moving electrons in it, so you can take advantage of that. Another way you can make magnets is by running current through a wire. If magnetism arises from moving charges, which it does, and current is moving charges, then all electric current creates a magnetic field. So what you're seeing up there is a bunch of little compass needles, kind of like I had over there. And what you can see, well, you can't really, I don't know how well you can see it. There's a, oh yeah, I've got a magnet in my hand. There's a wire vertically through this little set of compass needles. So I've got this array of compass needles and a wire vertically through it. And that wire right now does not have current running through it. I turn on my 12-volt battery, and I close this switch. Current will run through this vertical wire, and I should see the magnets line up. And they line up in a way that I want you to see, and the field is not quite strong enough in this demo for it to be really pronounced, but I'm hoping we can see it. And here's how they line up. Let's see if I can. I'm trying to like shuffle them a little bit. Then take this away, and I close it, and they line up. And the way they're lining up is in circles around the wire. Circles concentric to the wire. And that's important. And so when I have a wire like this, just a nice straight wire, the magnetic field around it is concentric circles around the wire. It may come up, it may be important to this class, so I'll mention it. The direction you can tell is if the current, see, this is black right here, so current is going down. Current's going down. If I put my thumb in the direction of current, thumb of my right hand, my fingers will sweep around in the direction of the magnetic field. So if I put my thumb down, my fingers will tell me which way the magnetic field is going. So it'd be little, what is that, clockwise circles around the wire. Okay. So one way to make a magnetic field is to just run current through a wire. Every wire that you've ever played with that had current running through it also had was creating a magnetic field. Now, that magnetic field, let's see if I can, let me try another example. I'm wondering if this will work. Okay, right now my current is not on. So you can see that compass needle. This might work. I haven't tried this yet. So I'm concentric around that wire. When I do throw the switch, concentric around that wire will be magnetic field. Compasses, that's the whole reason we ever made compasses, align with magnetic field. So if I close this, nice. So that compass is tangent to the circle around the wire. So there's a wire, you can imagine a circle around that wire, and that when I turn the current on, the compass needle is going to align itself to be tangent to that. Okay. I could even, let's see. Let's take 4 of these guys, then we'll move on. I have 4 tiny compasses. Let's see if that'll be demonstrated here. Probably should have practiced this ahead of time. You can't see those. Never mind. All right. It was going to be awesome, I promise. Okay. Okay. So anytime you run current through a wire, you're going to get a magnetic field. That magnetic field is usually not crazy strong. That magnetic field is usually not too crazy strong until you coil the wire to organize that wire. There we go. And that is called an electromagnet or a solenoid. And that's that. Notice, here's my permanent magnet. There's a picture of a permanent magnet, which is just a bazillion electrons all organized to create a net magnetic field. Here's the magnetic field due to a solenoid or an electromagnet, which is just a word for coil of wire. So a solenoid, electromagnet, coil of wire, it's all the same thing. And so here's why you organize wire like that, is because the magnetic field around just one wire is pretty hard to make strong. I mean, this might have been 20 or 30 amps, which made a nice enough magnetic field for demonstration purposes, but you usually don't have access to 20 or 30 amps. So what you do is you just take a wire and wrap it around 20 times, and I don't know if you can picture it. If you imagine, like I mentioned before, a wire has field going in concentric circles. Take that wire, wrap it into a coil, and the result is a magnetic field shaped just like that. And so if I want a magnet, I can go to the magnet factory and fabricate one, or I can just run current in a coil and I have the exact same thing. Okay. Question? Sure. Your thumb goes in the direction of current. So if you could imagine in this picture, oh my gosh, did I get that? Wait, is that possible the way I've drawn that? No, right? It would look like that. Wait, there. I got my arrow. I think I had my arrows there. So you can imagine current is going, I don't know if you can imagine, like current is going, yeah, okay. It's on the bottom, the current's going in. On the bottom, it's going in on the far side. So if you can imagine your thumb going on the far side, in order to get your fingers to be up in the middle of that coil, they would have to kind of loop around. Or you can imagine your thumb coming out of the top. Yeah, the top's also on the far side, and your fingers would have to wrap around and shoot out the top. I don't know if you can picture that. It's kind of hard to think about, but I don't even know if we need to know that. But yeah, thumb direction of current, fingers in the direction of field. Helps you figure out some stuff like that. Okay, so here's 2 examples yeah, these are actually both electromagnets technically. I guess all magnets are electromagnets. Here's a bunch of electrons organized to make a field. Here's a coil of wire organized to make another field. Our eye clicker is about the next example, so let's get out our eye clickers. And here's our first eye clicker of the day, and that is, where does our Earth get a magnetic field? Hopefully you know the Earth has a magnetic field. That's how compasses work. Discovering all the travel back in the day would have been a lot harder if we were on a planet without a magnetic field. There are planets without magnetic fields. We're lucky ours has one. It makes compasses work. Where does our Earth get a magnetic field? Permanently magnetized rocks in the core, or permanently magnetized rocks in the crust, flows of liquid rock in the core, or flows of electricity in the crust. Because she has it. 30 more seconds. Five, four, three, two, one. Nice. Looks like we were all paying attention, or most of us were paying attention in Earth Science class. C is the correct answer. I don't know if you, so it looks like 57% of us know this. Our Earth has a magnetic field. Not everybody knows that. Its magnetic field looks like that. It looks a whole lot like a bar magnet. And it gets it from the same place that all magnets get their magnetic field, and that's moving electric charges. Our Earth is not a big rock. It has flows of molten rock, charged particles in its interior, and those flows generate a magnetic field, which is useful for a few things. And by the way, here's also, let's see, another picture of it. It looks, so here's a permanent magnet. Here's a solenoid. Here's our Earth. They all look very, very, very similar. So our Earth has electric charges moving in its core, and those electric charges, just like any moving electric charge, creates a magnetic field. That's nice for a few reasons. Caitlin. It was C, moving molten rock in the core. So moving actual molten rock. So it's not like electricity running through it. Yeah, it's C. The answer. That's nice for a couple reasons. One, as I mentioned, it makes navigation, well, before we had GPS satellites, it made navigation possible. I guess we had stars. But the whole compass thing is pretty handy. When you're when you can't see the stars, you can get around with a compass. That's pretty nice. Also, our magnetic field shields us from cosmic rays. And so our sun, I think I've mentioned before, is constantly trying to kill us, sending us deadly charged particles all day long. Those charged particles, I guess I haven't mentioned this yet. So here's the whole picture of electromagnetism. An electric charge creates a magnetic field. A magnetic field pushes on a moving electric charge. That's this beautiful symmetry and this beautiful simplification that has happened with our understanding of electromagnetism. That moving electric charge creates a magnetic field. A magnetic field will actually push on a moving electric charge. So you get these moving charged particles streaming toward us from our sun and other cosmic sources all day long. Our magnetic fields divert them. And so as they come in toward our Earth, they actually get diverted by those magnetic fields. And if you were paying attention in Earth Science class, you might also know this. They usually get funneled, if you look at the shape of our magnetic field, they get funneled toward the poles. And so we have Aurora Borealis and Aurora Australis, and that's the glow that comes in the atmosphere as those charged particles go barreling into our atmosphere. We've got at the two poles, so if you're down in Australia or up near Norway or something, you can see the result of that, and that is the funneling of these charged particles being funneled into our poles and lighting up the atmosphere on the way down, which is pretty cool. Okay, Billy. That's not a dumb. That's a good question. Yeah, that's a very good question. So we talked about back several classes ago. We talked about that gravity is amazingly feeble compared to electromagnetism. So right now, my keys are being pulled down by the entire mass of the Earth. So million pounds of stuff is pulling down on my keys right now, and I can beat that with just my hand. And so the electrostatic repulsion between my keys and the hand is greater than the whole Earth pulling down. So it's very feeble. That's electric repulsion at a very close distance. The magnetic field generated by the flows in the core of Earth is really weak. So so you have to float a compass needle in a isolated environment on a very low friction needle just to get it to turn. And it turns reliably, but then you can beat it with something as big, as small as this. So our Earth's magnetic field, not terribly strong. I'm trying to think if you ever like, I'm trying to think of any places you see its result other than compasses. I can't think of one right now. So it's pretty weak. Just because the amount of current flowing is not strong enough to make it big, and we're far away from it. Yeah, good question. Okay. We're going to get there. We're going to get to start to talk about electric power. We have 8 minutes left. Okay, let's talk about that. Okay, so we know that electric charges create a magnetic field. We know a magnetic field can push on a moving electric charge. That's what is going on with the northern lights, aurora borealis. So the aurora borealis functions because this. I have a magnetic field that pushes on moving charges. There's another way to push on charges. One of the two things has to be moving or changing. So I either have a constant magnetic field like the Earth's and a moving charge, or I can just take a charge and subject it to a moving or changing magnetic field. That is how we generate electricity in most places on the planet. So a battery is a source of electromotive force invented by Volta, and it just pushes. It's electromotive force. It pushes electrons around a circuit. Here's another way I push electrons in a circuit. I subject my circuit to a moving or changing magnetic field. That's how we generate power, and that's also how. I'm trying to think we now have phones that charge just by laying it on a mat or something. I think my toothbrush charges just by sticking on some plastic base. Anything that charges without contact is similar. That I can push an electric current just with a moving or changing electric field, and that's how the power company does it. So I'll skip that icon here. Let's go straight to the power company. So here's how the power company does it. The power company generates electromotive force. In other words, creates voltage. They create voltage by spinning a magnet. That's the power company on the left. That's me on the right with my 120 volt light bulb. So the power company creates voltage. You got to think about where does voltage come from? Where does power come from? That's what the power company does. The power company spins a magnet past a permanent magnet. They spin some type of magnet past a coil of wire. So just a wire period would work. And so they take a permanent magnet or an electromagnet, doesn't matter, and they spin it. The reason they spin it is because you need to move or change the magnetic field. Take a spinning magnet, put it near a wire, current will flow in that wire. So how do we make power on this planet? Let's go through a couple options. Hydroelectric dam spins a turbine, which spins a magnet. Coal, burn coal, get heat, boil water, use the steam to turn a turbine, which turns a magnet. Nuclear power uses nuclear fission to create heat, to boil water, to turn a turbine, to spin a magnet. Geothermal, get something really hot, make steam, turn a magnet. You get my point. There's all these ways we create electricity on this planet. Almost all of them is just we're trying to get something to spin our magnets. So we can burn coal to spin our magnets. We can burn natural gas to spin our magnets. We can use water. We can use wind, same thing. Put a big windmill up. Get that to spin your magnet. We need something to spin our magnets. The only thing off the top of my head that's not that is solar. Solar is just bam, energy. We got it. That's why solar is the best. But pretty much everything is just us trying to get something to spin our magnets. And here's the upside of that. The upside of that there's a couple downsides, but it's pretty much an upside. The upside of that is the result of a spinning magnet creates fluctuating field. Let's see, I'm going to pull my toaster picture up. It creates fluctuating electricity. And it creates sinusoidal or AC voltage. So what the power company is doing, the power company is spinning a magnet. And they're either using nuclear power to spin their magnet, or they're using coal to spin the magnet, whatever. But the result is a spinning magnet. When you get something spinning, you get this cyclical, sinusoidal, wavy shape of voltage coming out of it. And that's what they send on the power lines, and that's what comes out our walls. Our walls have a constantly varying voltage. In America, it's going up and down. By the way, here's a little bit of trivia for the day. The up and down, so that wall is rated at 120 volts. 120 volts means it oscillates between 170 and a negative 170. It goes up to 170 and down to 170. The average of all that is about 120. So that's why we call it 120 volt plug, is because we average it using something called root mean square, which we don't even know. And then we get 120. So the power company spins a magnet, creates a varying voltage. That varying voltage shows up at our house as a sine wave. I think we have time. Let's do one more demo to show why that's nice, and then we'll be done. Show one more demo why that's nice. I have up here, where's my paper clips? Paper clips. I have a paper clip. Okay, there they are. Here's my paper clips. I have up here what's called a solenoid or an electromagnet. So I've got in my just a coil. This is nothing more complicated than a coil of wire. And so when it's on, I can stick. See, I'm gonna change the camera angle. We have 2 minutes left. Okay. When it's on, my paper clips will align to the electromagnetic field. So here's my paper clips all trying to align themselves to my electromagnetic field. But that's all this is a coil of wire. But here's what's nice about that. This electromagnet is actually flipping north-south, north-south, north-south 60 times a second. Then I let go of the button and it's off. Okay. So this electromagnet is flipping north-south, north-south 60 times a second. Here's why that's nice. Here I have a light bulb. I have a light bulb connected to a coil of wire. If I were to put that near here, that's not going to do anything. But this magnetic field, when I push this button, this magnetic field is alternating 60 times a second. If I subject wire, just like the power company does, to an alternating magnetic field, that'll push current in here. So this is not connected to a battery or anything. This is just a light bulb connected to a coil of wire. That's it. But when I put this nearby, I can actually get the bulb to turn on. I can get the bulb to turn on simply by subjecting it to an alternating magnetic field. So this is just a coil of wire, just a solenoid. And when I flip that magnetic field back, and that's the key. The key is right now, you can almost hear the buzzing of my paper clips. My paper clips buzz a little bit because they're flipping north-south, north-south, north-south 60 times a second. It's not enough. It's fast enough that the paper clips don't fall off. They don't care whether it's south or north. They're attracted to either. But that flipping can be used. That flipping can be used to light the light bulb just by. Here's our last term for the day when we'll pack up. Just by induced electromotive force. I'm inducing electromotive force or induced voltage in that circuit. Okay. See you Friday.